Good afternoon. We're back for another day of image processing. And today we're going to pick it up with the remaining material in the section on color and human perception, which is opponent color spaces. So let's get started. So what happens is that so far we've learned about the tristimulus color spaces. If we could switch to the slides. Yeah, we've learned about tristimulus color spaces, and basically any invertible linear transform of a tristimulus color space like RGB or XYZ is a legitimate representation of the perceived colors from the point of view of color matching. But it's not necessarily the representation of color that captures the aspects of how people perceive relative differences in color, or how they sort of process color cognitively, or sort of the level of perception. So it was found a long time ago, and I think one thing maybe that's coming out, comes out of this material is that there's no single correct coordinate representation of color that works for all applications. It depends on what you're doing. For instance, we're going to see that if you want to represent the filtering of color data, often you want to use it in a linear coordinate space. But if you want to see the quantify perceptual differences in color, then that may not. Linear spaces are almost never the right thing to do. In fact, we said that one of the things you're supposed to always remember if you come out of this course is don't quantize data that's in linear coordinate systems, because you'll get quantization artifacts. So for that, we saw that gamma correction was good, right? So, when do you want to use gamma correction? When do you not want to use gamma correction? What color coordinate space is best? Well, there is no uniformly best color coordinate system for all applications, but if you want to represent how humans perceive colors, then opponent systems are sort of a better representation of that, and in a variety of different ways. So the standard opponent color system is are what's called red, green, blue, yellow channels. So the thinking is that at some very simplified level, the color information that your retina obtains and then is sent up to your visual cortex is represented as a luminance channel and a red-green color channel and a blue-yellow color channel. So you can obtain those by, in a very simplified sense, subtracting the green from the red and the blue from the yellow. So, and that's why I think I asked you earlier. I said, is there such a thing as a reddish green or a bluish yellow? That doesn't sort of perceptually make a lot of sense. Okay, I mean, it's difficult to. I mean, you can certainly take blue and yellow and mix them together, but if you add blue and yellow, you'll just get white. But if you, and this is why if you take blue from white, it's surprising that you get. Well, let me see. If you add red and green, you get. If you add red and green on a display, you get yellow. And that's, at least to me, surprising, because yellow is not perceived as the combination of red and green, because it's a different axis, essentially. And that's why, in a kind of a simplified sense, that's a surprising result. So humans sort of perceive colors as reddish greens and bluish yellows, and that's not just, some things are learned culturally. Well, the current state of the art in science is that, some concepts of colors are cultural. So in certain cultures, certain colors are maybe preferred or described in more unique ways. They're learned as opposed to innate. But the red, green, blue, yellow difference is believed to be, hardwired into your brain. So it's not a learned behavior. And you can actually do psychophysical experiments where you ask people to identify things like red, okay? And your perception of red is, so that's different than just a color matching experiment. That's a color perception experiment. And red is a uniquely determined thing that's a result of the way you're wired up. Okay, so now it turns out that the color transform that puts you into this opponent space isn't completely invariant to everything, right? I mean, it depends on a lot of things. It can depend on a lot of things. It can depend upon your adaptation, which could depend upon the illuminant, or all kinds of complicated things. But there are some sort of nominal transformations that put you into an opponent color space, approximately. It can also depend on frequency and so forth. But we'll refer to the opponent color spaces coordinates as 01, 02, and 03. So 01 is the luminous, 02 is the red-green, and 03 is the blue-yellow. Now, so the idea with the opponent color space is that one of the most important reasons from an engineering perspective that opponent color spaces are important is that the modulation transfer function for the three spaces is different qualitatively. So we talked about modulation transfer function. You went through that. I don't think I was here the day that you went through that, right? Let me just do a quick review because it's really important, and I want to also emphasize a couple things. Let me see if I can find the slide on that. Just a minute. Let me see. Oh no, was I here the day you did that? Okay, so when you measure modulation transfer function, you present a grading, and the contrast of the grading is the ratio of the variation in the brightness or whatever to the lightness. Say if it's in energy coordinates, this would be the something proportional to y in the XYZ coordinate system. So that variation divided, and then there's some average level, so the background level, because this has to be positive. So the ratio of that change to the average level is the contrast. So you're looking at the function of the contrast sensitivity as a function of spatial frequency, where spatial frequency is in units of cycles per degree. Because if you put the person further away and you assuming that the person's vision is corrected appropriately, and that you're not so close that the material's out of focus. So then if you take the person, you move them further away, and you scale the material up, then sort of everything remains relatively the same. So it's actually the angle subtended per cycle that's the relevant quantity. So the units that make this kind of a meaningful measurements are contrast sensitivity in units of cycles per degree. So cycle per degree would be the degree subtended in angularly, and the contrast sensitivity is 1 over the just noticeable contrast. So if the just noticeable contrast is, I'll just make up a number, 0.1, okay, so that means you need a 10% change in the signal in order to be able to see it, then the contrast sensitivity would be 10. So the larger the contrast sensitivity, the more sensitive you are. So when you do a curve based upon that, let me show you the achromatic case first. You get a curve that looks like this in concept. This is kind of a factoid plot like you would have in USA Today, okay, but it gives you the concept, okay? So this unit cycles per degree. Oh, and basically, by the way, an important fact is that the conversion factors, when you want to go from cycles per inch to cycles per degree, right, you take the distance in inches. So It doesn't have to be inches. It can be any units you want, but the units of frequency have to be per that unit. So it would have to be cycles per inch or cycles per centimeter, and then D would have to have the corresponding unit of measure, which would be inches or centimeters. And then those units cancel out, and it works. But the conversion factor is pi over 180 times D. And when you multiply that, so this is an important formula. When you multiply by that, you convert from cycles per inch to cycles per degree. Sometimes people, in imaging systems, people will talk about dots per inch, or sometimes you hear spots per inch. That really is usually meant to represent the equivalent concepts of cycles per inch. But since we're signal processors, we'll just talk about cycles per inch. So when you plot that, you get a curve like this, because when the contrast sensitivity is larger, it means you're more sensitive to small variations. So if the contrast sensitivity is, let me just make up a number, 50, it means you can perceive, you are sensitive to, you're just at the threshold of being able to perceive a 1/50th change in the signal, a 1 part in 50, a 2% change in the signal. So what happens is that the concept is that at very low cycles per degree, you become insensitive in the lightness channel. And at very high spatial frequencies, you become insensitive. This part here is, well, first of all, it's difficult to measure because you move your eyes. Those are called saccadic motions. I'm mispronouncing it. So your eye just moves around. If you could stabilize the image on the retina of your eye, the image would disappear, because your retina, the cones in your retina are not sensitive to like a constant input. In general, humans perceptually tend to be insensitive to any kind of stimulus which is persistent. Okay, so if your kids are saying they want to go to ice cream over and over and over again, eventually you'll not hear it anymore. Okay, so you need to have some variation in the stimulus. Okay, so at the low spatial frequencies, you're not getting a lot of spatial variation, but your eye will move around. So this isn't a difficult experiment to formulate. Although I think there's a classic experiment that you see sometimes in these science museums. I remember seeing it many years ago in is it called the Exploratorium in San Francisco? I don't know if anybody's ever been there. I assume it's still there, but it was a science museum, and what they do is they paint a gradation. Okay, so this side is, say, a little bit darker than that side, right? And then what they do is they hang a big fat rope in front of it. Okay, so when the big fat rope is in front of it, you can't see. It looks like the two sides match. Also, what happens is that if you plotted the gray level on the two sides, it's like this. Say. Okay, so when you put the rope there, but it's such that the rope is not so thick that it's not just eliminating the variation. But when you put the rope in front of it, you can't see it, because because the frequency associated with the variation is a low frequency. And when you take the rope away, you suddenly see, oh my goodness, there's like this sharp change, and then it's clear that the two sides look like a different gray level. Okay, so that phenomenon exists, but it's not so important in electrical engineering, electrical and computer engineering, in engineering applications, because usually the part that's more important is this part, for a few reasons. One is while this phenomenon is definitely true, it tends to not exhibit itself in simple ways, and the other thing is that the low spatial frequencies in data tend to be less important from an information point of view, because the amount of information in the low spatial frequencies is smaller. It's the high spatial frequencies that contain most of the information in the sense of information theory. Okay, so if you're coding an image, the number of bits it takes to code this part is pretty small, So it's not that important. So in coding and transmission applications, this isn't so important. It's nice to know it's there, but it's not that critical. So this part is very important, because if you didn't have a roll-off, it would take an infinite amount of information to code the data to required precision, right? You'd have to just keep going higher and higher spatial frequencies. So what happens is at high spatial frequencies, you become less sensitive. This is very intuitive, right? Because if you're for instance, all this says is that if you try to read text, so if I take this page of text and I hold it a mile away, are you going to be able to read it? No. Okay, because the spatial frequency in terms of, now the spatial frequency on the page does not change in units of cycles per inch. Obviously, just because I held it a mile away doesn't change anything. But what changes is that the spatial frequency in units of cycles per degree so the way it gets mapped to your retina changes, and the frequency is too high for you to be able to see the contrast change in the text. So essentially, it's like a low-pass filter, and the information's lost. Okay, so yeah, I'm just trying to think if there's another point I want to make. So, right. So if you hold something further away, it maps to higher spatial frequencies, right? Closer, it's going to be lower spatial frequencies in cycles per degree. Now, what then happens is that so with the Oponent color system, the spatial frequency response. The spatial frequency response is different for the three channels, qualitatively speaking. So first of all, the luminance channel has what is called a bandpass response. So it has this effect of being high pass. So below some spatial frequency, you lose sensitivity. For the chrominance channels, that's not. I mean, this is an idealization of reality, but that's not supposed to be true. That at the low spatial frequencies, they're not supposed to drop off. But they do drop off more rapidly at the higher spatial frequencies. And that's a result of a lot of things. It's a result of chromatic aberration in the optics of your visual system. It's also a result of the fact that you have fewer cones in your retina for instance, the short wavelength cones. So you just have less information, and it's not entirely clear whether that's cause or effect. And by the way, there are psychophysical experiments that people perform where they can separate out those effects, but it's tricky. So in other words, they can use some sort of complicated optics to put the right chromatically correct signal onto the retina, and then see how much of the low pass draw. This is sort of the aggregate modeling of the overall visual system, but it's really a result of two things. The low pass effect due to the neural processing, so there's some sort of reduced bandwidth, both through the reduction in the number of cones and the way the information gets passed on, and the optics, right? The optics is more accurately modeled using very simple, well, not very simple, but very well understood physical models of light propagation and optics and so forth. When you get into the neural system, things start to get more complicated. But so there's two effects, and the neural part of it is effectively nonlinear, because, or at least has the potential of being nonlinear, whereas the optical part of it is linear in energy, right? Because we know exactly, to a very high precision, how photons interact when they pass through the optics of the lens and are absorbed and detected by the retina, the cones in the retina. But after that point, the things get less, more difficult to model precisely. So you can put those things together, but and what ends up happening is that there's really essentially two boxes that process in serial. There's one sort of simplified model of reality. All these things are models of reality, so they're not perfect. But over here, this is the optics of the eye, and this is the retina and the optic nerve, and then visual cortex. So this is all the neural processing, and this is nonlinear in general. I'll put here in general. And the reason I'm putting in general is it doesn't have to be nonlinear, it just can be nonlinear. But this part here, the optics, is linear, at least to a very high accuracy, because it's optical propagation of light, but I'll put here in energy. So if you're processing the data in linear units proportional to energy, which would mean x, y, z, right? So this would be x, y, z. If it's not by linear, I mean that the variables that represent the data are linearly proportional to the number of photons. Is that true for gamma-corrected RGB? No, it's not linear. So here, modeling this low-pass filtering is appropriately done in a linear coordinate system, and here it's appropriately done potentially in a nonlinear one. But this one's first, so in some sense, that could be made more precise. It dominates just because it's first, not because it's a stronger effect, but just because it's first. So so this low pass effect is a combination of those two things. And the red-green and the blue-yellow have substantially less bandwidth, but of the two, the blue-yellow has less bandwidth than the red-green. Okay, so the practical result of this is that when you code images, often you usually subsample the chrominance channels at less spatial frequency than the luminous channels. So that means you don't have to retain as much data. If you're doing, like with the JPEG lab, you'll talk about using DCTs. If you're doing the DCTs of the chrominance channels, you subsample them typically 2 to 1 in the X and Y direction. So you represent them with 1/4 the amount of data. A typical JPEG image is encoded with a fixed resolution, and whatever resolution is chosen, say like it's just nominally, it's 512 by 512 resolution for the luminance, and then the two chrominance channels are both encoded with half the resolution in both directions, so it would be like 256 by 256 in both directions. So the total number of bits is going to be the luminance channel plus 1/4 the number of bits for the two chrominance channels, but there's two of them, so it's going to be 1 plus 1/2 nominally. Now the two channels may compress differently, so the aggregate number of bits changes, and that's called 422 coding, I think is the standard nomenclature. But in any case, it takes advantage of this important curve. And in fact, it's a bit crude because the subsampling in the two chrominance channels is the same, even though the bandwidth is different in these two channels. But the quantization matrices for the two channels can be different, so you can exploit that. So this has a lot of practical implications that are important in processing of images. And so another thing it tells you is that, well, the blue-yellow channel is, if you wanted to present some information to be visualized by a person, right, then and it was high spatial frequency information, you wouldn't want to put it in the blue-yellow channel. So the blue-yellow channel is okay. So an example of this would be that. So the blue-yellow channel is if you put see white. Okay, if you put white text, if you put a white background and you put yellow text, right? And then if you wanted somebody to be able to clearly see something on a street sign that was far away, would you use yellow text on a white background? Intuitively, that's a bad choice, right? Or would you use blue text on a black background? Intuitively, that's a poor choice, right? Now, it turns out that many color scientists don't necessarily know this because they make their PowerPoint slides like this, okay? And then you can't read them in the presentation. But, you know, hey, what am I supposed to do about that? Okay, but anyway, yeah, so it is a little counterintuitive, though, because you'd say, well, hold on for a second. If I put blue text on a yellow background, that wouldn't be so bad, right? That should be visual. I should be able to see that at a distance. It might not be good as black on white, but it's not so bad blue and yellow, right? So, hey, what's going on here? You said this was the blue-yellow channel, okay? Okay, now so what's the paradox? Okay, well the paradox is this: blue-yellow channel means that you created the channel by subtracting blue from yellow. It doesn't mean that by varying between blue and yellow, that's the only channel that will be stimulated. So it's the difference between the rows of the color matching functions and the actual color. Color matching functions are a function, and colors are spectral distributions, right? So yeah, the problem is blue and yellow generally don't. Usually blue is a dark color, that's to say, blue has a relatively small amount of luminance in it. So the other way of putting it is, if you go back to the equations for calculating y, the equations for calculating y have a relatively small coefficient for the blue channel. So even if you go back to here, this was the universal coefficients for computing the so-called Y component in NTSC video from the red and the green and the blue, and this coefficient's small compared to the green, which is the largest, and the red, which is next. Okay, but the blue is generally small. So the interpretation of that is that blue has a relatively small luminance component. So if you have a blue, a blue on a, okay, hold on. So if you have a blue and a yellow, the blue will have low luminance and the yellow will have high luminance because yellow is red and green, okay? So this is not isoluminant. It's to say, by saying it's not isoluminant, what you're saying is that it will stimulate the luminance channel. In order to produce something which is isoluminant, all right, and has no red-green component in it. Well, to make it isoluminant, you would take white and yellow. Now, the yellow, if you remove the blue from white, is going to be a little bit darker, so you would reduce the brightness of the white. And you get an isoluminant match, and then you would have been able to produce something that no one will be able to see very well at a distance. So what you could do is, I can write, the solutions to the exam on this, put them far away, and then when you complain you didn't know how to do it, I could say, well, you should have just read it. And you'd say, well, but I couldn't read it because it was isoluminant, But then the judge wouldn't understand that, and it would all get very muddled in the end, so I'd win. Okay, but anyway, the black-blue is a similar kind of thing, right? Because if you can take, well, instead of black, it could be a gray. So you just have a dark color. And then the blue, and then it would be isoluminant, stimulates the chrominance channel, and your ability to perceive high spatial frequencies would be poor. So that's kind of the idea there. There is a bunch of stuff that I'm not being extremely precise about, and it gets fairly complex when you really want to do these kinds of experiments, especially because you have to define contrast precisely in the color space, and that gets a little tricky. But these experiments have been performed. There's been a lot of research done in this over the years, and it's very important when you're actually processing images at times to use opponent color spaces. So now here's just I have in the notes some color spaces you can use. Okay, this is not. Okay, the operative word here is approximately, because it turns out LMS, well, first of all, LMS is not an opponent color space. LMS represents this is the color space that would result by using the actual long, medium, and short cones of the retina, if you had omnipotent knowledge of their color matching functions. Okay, so LMS would be the relevant primaries associated with those color matching functions. Well, these are the tristimulus values that would result by using the those color matching functions. It turns out that LMS is a standardized color space in that in the psychology community they've tried to measure, quantify the color space, the color matching functions associated with the long, medium, short cones for the sort of standard observer under some standardized conditions. But that was done independently of the CIE color matching standards. So there is no transformation that gets you exactly from XYZ to LMS. Because they're just, they're essentially incompatible in the sense that the color space, if you take the color matching functions of XYZ and the color matching functions of LMS, they don't span the same space in the spectral domain, the 31-dimensional spectral domain. So they, but they're close. Okay, the two color spaces are close. So you can approximately get one from one, and here is just some calculation I did, which gets you from XYZ to LMS. And then, so psychologists often work in the LMS domain, and like one example is this Oponent color space of 1 del, where he defined it relative to LMS. So this would give you an Oponent color space once you get into LMS. And here I give some citations to work. There may be newer stuff, but some work that's been done in the basic psychophysics of quantifying Oponent color spaces. What I do want to mainly do here is the main application of all this is when you're trying, or a primary application from the point of view of engineering and designing of imaging systems, is when you want to have perceptually uniform color spaces, or when you want to measure, color fidelity, or you want to have image fidelity metrics. Perceptually uniform, no color space is going to be perfectly perceptually uniform, but some are better than others. And XYZ is terrible, as I pointed out previously, right? It's not even a little bit perceptually uniform. So that's this plot right here, where we saw that the ellipses change in size dramatically. So mathematically, this is very useful, but it's not perceptually uniform at all. So you would not want to do quantization in this space, right? So two commonly used perceptually uniform color spaces are LAB and LUV. And of those, I think LAB has really become much more popular. So the way it works is, well, first of all, you want to do gamma correction, because from the very beginning we saw that gamma correction has the advantage of taking into account contrast. So it helps account for the fact that you're mostly sensitive to contrast. So, and it's been widely accepted that using a gamma of 3, what I would call a gamma of 3, is a good approximation to a perceptually uniform color space. It's not exact. So, and then LAB is normalized by some white point. And a typical choice would be D65. But if you get LAB, you need to verify what white point was used for its encoding, because it's not part of the standard. I mean, LAB can be used with any white point in principle. So these are the formulas, but they're inexact, approximate formulas, because if you remember, the gamma correction is not done this way. It's done with that, complicated function, which is linear for very small values, but it approximates this power law function. I'll give you the exact formulas in just a minute, but it's easier to look at them this way just to get the intuition into what's going on. So basically, you gamma correct the x, y, and z components. Remember, Y looks like luminance, and then X and Z. So you can sort of think of Y as like green. You can think of X, Y, Z as like supersaturated red, green, and blue very loosely, okay? Particularly the Z is like the blue and the Y is like the red. So you gamma correct these three components, and then you form an opponent color space by subtracting them. So it's kind of a nonlinear opponent color space. And you multiply A and B by, 500 and 200. So the fact that A is larger than B makes sense because A is the opponent space associated with green minus, so let me see, that's green minus red. So this is like the red, this is the red-green opponent, red-green component, opponent coordinate, and this one is the blue-yellow. So the blue-yellow is less important than the red-green in that it falls off more rapidly and you have less sensitivity because you have fewer short cones. But what's a little bit surprising is that L is smaller than, the component here of 100, L is smaller than A and B. So what that says, that's sort of an interesting, that's sort of an interesting result of the fact that color is, LAB is designed to measure differences in colors in applications where you're using the color over a large field of view. So for instance, people would often use something like LAB to specify colors in manufacturing applications where they're going to make they're going to make a carpet, or they're going to make a plastic panel, or something like that, and they want to specify to make sure that this color is correct. So when they manufacture it, they specify to their supplier the color that's supposed to be in LAB. So these are large areas. So the modulation transfer function, you're at low spatial frequencies, is the assumption. So at low spatial frequencies, these numbers, relative values, are reasonable. But when you get to higher spatial frequencies, they get out of sync quite a bit because these roll off much more rapidly than the luminance component. So if you try to use LAB for, if you try to convert an image to LAB and then encode it, you won't get very good results. You'll actually get very terrible results. Okay? It'll be a lot worse than having done nothing. Gamma-corrected sRGB is much better than LAB because a lot of the artifacts you get when you code an image are at high spatial frequencies. So the relative weighting of these three numbers is really far off. But if you're trying to match colors where the spatial frequencies are low, then LAB is an appropriate choice. And what the convention for measuring changes in LAB is delta E, which is just the Euclidean norm in the LAB components. So people would use LAB, for instance, if you're trying to match colors between a display and a printer. That would be a typical application because color shifts between the printer and the display have a low spatial frequency, so there that would be an appropriate use. But trying to use it for coding an image, well, that would be an inappropriate use. So these are the exact formulas. I won't belabor them because they're just the application of this particular function here to the gamma correction. So it's just like we had gamma correction formulas for sRGB. Okay? Okay, I think I've already mentioned this. So LAB is appropriate. It's very good for measuring color differences in objects. It's the standard for measuring, say, paint colors. There's some specific applications. So LAB is widely used. You can use it with the different XY, like the 2-degree or the 10-degree observer in the CIE, but and you can, in principle, use it with different white points. But LAB is widely used for these kinds of applications. But it's not good for transforming an image and then encoding it. And the reason is the high spatial frequencies, as I said, are not well modeled because it doesn't incorporate a model of the contrast sensitivity function as a function of the spatial frequency of the distortion. Okay, so so you can incorporate this kind of a little more sophisticated. So the problem is LAB. One possibility would be that you would take, if you wanted to know that if you have two images, X of MN, right, and you have another image, Y of MN, and you want to say, well, how close do these two images look to each other? One possibility is that you would compute the LAB for both images, and then you would subtract them. So this would be plus minus, and then you take this and you take the norm squared, or you take the norm, right? So the norm would be, this is delta E, and you'd average. That's a problem because it's not accounting for the fact that whether the distortion between these two is high frequency or low frequency. If it's a low frequency error, then this is an appropriate thing to do. If it's a high frequency error, it's inappropriate, and the reason is that the spatial frequency modulation transfer function for the chrominance channels tends to fall off a lot faster. So somehow you need to compensate for that. Now, there's been an enormous amount of work in image fidelity metrics, and things get very sophisticated because fidelity of an image can depend upon a lot of things. It can depend upon, this relates to the entire, issue of color appearance, which we also talked about at the beginning, where I showed you the two images, and in one image the same color looked, I think, blue, and the other one it looked yellow, which incidentally are opponent colors, so it's the worst case scenario, right? To the same actual stimulus appears as two exactly opposite colors, right? It's like your bank account went from positive to negative without you doing anything, okay? So here with color fidelity metrics, but there's some simple things that can be done short of a perfection and can be used. There's this, and basically what they do is the idea is to try to incorporate some spatial frequency response modeling along with LAB kind of modeling and sort of merge them together in an overall system. And there's been a variety of attempts to do that. And but the basic idea is this. And let me just show the flow diagram. Okay, so what you do is this. Hold on. Okay. Okay. Well, yeah. Oh, okay. Hold on for a second. No, this is, did I have the right slide here? Okay, so you take, wait, just a minute. Okay, so one possibility is this. The problem is this. Let me just draw this. Okay, what you could do is this. You could take X of Mn, okay, and you could take Y of Mn, and you could put this into a box which takes which converts to LAB, and converts to LAB. Right. And then from here, you could try to put a filter, spatial filter. And here you could try to put a spatial filter. And then you could try to subtract these. And then you could take a norm, say, and then you could average. The problem with this is now you're applying a filter which has been after the LAB is computed. And the LAB is a nonlinear transform. So assume this is linear here. The problem is you really want to always apply this filter in a domain which is linear with energy. And the reason is this plot here. That the human visual system, the first thing that occurs in the human visual system pipeline is the optics of the eye. So if you're looking at, when you did the lab for gamma correction, and you looked at a grid of black and white dots, the average you saw when you view that from a long distance is caused by the filtering, is the result of what happens but when you're blurring to the optics of the eye, and then you see the overall light field in your retina, right? So the averaging here that occurs is a filter that's applied in the linear domain. If you apply the same filter in the gamma corrected domain, you'll get a different result. And that's how you were able to use that sort of clever aspect of your eye, how your eye functions, to actually estimate what the gamma of the display is without any physics, without any measurement instruments. You didn't have a spectrophotometer or some kind of special piece of instrumentation. You just use your eye as the instrumentation. Okay, so this is a bad idea. You don't want to do that. If you do the filtering after LAB, you'll get the wrong answer, because you won't appropriately account for what you would actually perceive as the average. Okay, and that effect was actually used to get the answer. So it's a strong effect in the lab, because that's how you calculated gamma. Okay, so you really want to do the processing in the linear domain. So here is one possible way. You take the two images that are in RGB. They can be in if they're in linear RGB, that's fine. If they're in sRGB, gamma corrected sRGB, you have to remove the gamma correction so that they're linear. Okay. Then you do a transformation to an opponent color space. So in this particular example, it was done by transforming to something we call YCXCZ. So YCXCZ is, what you do is you take, basically you just take the nonlinear part out of the LAB calculation. So now this is a linear coordinate system. Yeah, it could be some other opponent color system, but this is an example. Then you apply filters that are appropriately chosen for those. These are low-pass filters, and the low-pass filter for then the CX and the CZ coordinate has a lower cutoff frequency than the Y. Then you transform back, and you go to LAB. Now it's been appropriately filtered, and in the LAB space you subtract, you take the norm, and you average. This isn't perfect, but this will give you a much better result than you would get if you tried to just do the LAB directly. And it'll give you a more accurate result by applying the filters in the linear domain than if you applied them in the LAB domain. Okay, so this is just kind of more of the same. Here are some particular filters that have been used. This is kind of all the literature. Like I said, there's a lot of work that's been done on image fidelity metrics, but these are examples of sort of simple fidelity metrics that can be implemented with just some filtering and some nonlinear transformations. And here are some filter responses that have been kind of widely used by Nason and Sullivan. You can look these references up if they're interesting to you. But, okay. Now, one other thing that comes up is that in some applications you want these fidelity metrics to be efficient to compute. So you don't want to have to actually compute LAB, because that's very computationally expensive. So if you design this algorithm, if you design this metric of fidelity into some other algorithm, like a coding algorithm or a halftoning algorithm, we're going to talk about halftoning later, then you can simplify it by just applying the filters in the linear domain and computing, this should be a sigma here, and computing these sums in the linearized domain without using the LAB transformation. But then you're not, without the gamma correction, you're not accounting for the fact that your sensitivity, contrast sensitivity, could be much higher in dark regions than in light regions. But, it's an approximation you can use depending upon what the application is. Okay? Okay, so let me just well, there's only exactly 1 minute left. But let me just do a quick example. You did this in the lab, but let me just go over again. So if half the pixels are black, I may not get this done, but I at least want you to leave with this thought. If half the pixels are black, okay? Oh no, I put it in the wrong place. If half the pixels are black, the average luminance you'll see if you're far away would be 1/2. because the amount of photons that would hit your eye would be 1/2, right? But the gamma corrected value that you would see would not be 1/2. So just go back and think about that. That's a typical exam question, by the way. Okay? All right. Thanks a lot. See you next time. Bye.